Hi, so I'm going to talk about how formal specifications can be used in the nuclear industry. I think my title, I think it would make sense, is I need to acknowledge ChatGPT for coming up with a title. So I'm going to tell you a bit who I am, where we come from, tell you about nuclear power plants and what digital systems they've got inside, and why the word pressure is in the title. And then we talk about architecture of digital systems, and to give you some examples of things that have been done or can be done or are changing, and where I see it going from here. So I'm from Adelard, which is part of NCC Group from 2022, so a couple of years. And we look at supporting clients achieving safety, security, dependable systems. So things that they behave as you expect them and we want them to be. So cyber is part of it. Clearly, if it's not secure, it's not going to be safe and it's not going to be dependable. And also we've got a platform to reason and help us thinking about these things and communicate them. So we work on lots of different systems. So I'm going to talk about nuclear power plants, but we also work on defense and control and transport, medical devices, autonomous systems, and also security products. So pressurized water reactors. So this is a type of nuclear power plant. It's the most common type of plant in the world at the moment. So you've got the nuclear rods here that heat up water. There's a pressurized, so the water doesn't boil, so it keeps being liquid. And there's another circuit, water that is heated up, makes a turbine spin and generates power. So this is how pressurized water reactors sort of work. So in terms of architecture, digital architecture, this is the design of the EPR, which is plants being built in Hinkley Point and other parts of the world. This is the UK. I think this is the UK design. It's all slightly different. So the level 0 is the sensors and the actuators. So this interface with the plant physics. Level 1 is automation, and level 2 is where the human machine interfaces and human operators are. So in terms of the level 1, there's a three parts. We call it defense in depth because we don't want power plants to go bang. So the preventative line, it looks, monitors the parameters, and it tries to keep them within certain limits. If things go outside the limits, then is where the main line comes up and typically shuts down the plant. And then if all of this fails, then there's the last one, is risk reduction, to try to minimize the risks of a core melt and accident. So if you see here, there's different boxes with different platforms, basically either non-computerized or PLC based. So in terms of digital systems, so mainly PLCs, SCADA systems. For the EPR, there's two types of platforms. There's Telecom Access, which does the most critical part of the plant. So there's different criticalities on different systems. And then there's another PLC that is based on the S7, is Siemens Q2000. So more digital systems is that all of that relies on information. So about temperature, about pressure, about radiation, and also reliable electrical systems, so UPSs, relays, voltage regulators, etc. And lots of them are digital, so lots of them have software or inside. So smart devices, we talk about smart devices. This is how we describe this type of systems that are commercial off-the-shelf, come as box, limited functionality. You can't program them. You can configure it, but they come ready to be used. And we've done lots of work on looking at that. This is a selection of some of the smart devices I've worked on. So both types of digital, or all types of digital systems in a plant that needs to have a safety function needs to be justified. So part of the licensing conditions that to operate a plant in the UK, you need to demonstrate that this is going to be safe. And that's typically done using safety case, which is a set of documents or document that shows how it is going to be safe during all the life cycle, lifetime of the plant. So from design construction to commissioning operation and then decommissioning. So typically to do that in the UK, there's the UK regulatory regime, so they describe on the ONR, so ONR is regulator, Office of Nuclear Regulator. They have safety assessment principles, call it SAPs, and for digital systems they have two parts. So I'm not going to spend a lot of time on this, but one part is a production excellence. It's saying, I've developed this using the relevant good practice, the way that people should develop these systems. So consistent with current standards, we've got a good quality management system, and I've tested everything. And then the other part is independence, confidence building measures. So independence of how you develop, someone independent from your development team comes and does additional challenges and checks to show that your system or your component behaves as it should do. So I'm going to give you two examples, one smart, one PLC. I think I overdid a bit the QR code, so apologies for that. But this one is actually points out to a paper that describes this work that we've done. So this is a smart device. This is, actually it's not a PWR, it's a BWR, so it's a boiling water reactor. And it was designed by Hitachi, that he went through assessment to be built in the UK a few years ago. And part of this work, they needed to demonstrate to the regulator that they knew how to assess smart devices. So we did a pilot study to demonstrate how we did that. This is a temperature transmitter, so it's got lots of different potential sensors that you put in one end, and then you produce a 40 to 20 milliamp output depending on the temperature. So typically, most of the smart devices, all these things, they're quite fairly simple. Not all of them, but most of them are fairly simple. They have some inputs, and then they do some math, and they, from some calculations, get an output. And then some interrupts that come with doing different things. But that's typically the structure of the code. So the way we think about these systems and how we're going to trust them, we try to look at different aspects of how do we develop this safety justification, what we need to consider to build trust and to know that they're going to behave as you like. And I tend to think about safety assurance based on these three different aspects. So one is, okay, did I do what I was supposed to do? Do I know what good practice is? Did I follow the right processes? And then the other part is a property base, is to say, have I demonstrated the functionality and the time response, and does it do what I want it to do? And in terms of vulnerability, it's a bit broader than just security vulnerabilities, but what are the type of things that can go wrong with the type of systems? So the reason why I put this triangle here is because I wanted just to highlight the functional analysis was just one aspect of the overall justification. And we use it in this case, it was to show the functionality, so it does the functions accurately, but also to look at absence of runtime errors, for example. So in this case, what we did was use pharmacy with and Jesse alter ego. I think Jesse is not really supported anymore. But what we did was we focused on specific functions that were critical for the smart device and proved them correctly. So Some of the challenges of doing this type of work, I think, which I think is important when we think about verification and specifications in scale, is that a lot of these components are commercial off-the-shelf, and they're used in lots of industries where people are just happy to take them and use them. And to be able to do that, you need to go and ask them nicely, can I have your specs? Can I have your code? Can I do these things? So you need a lot of collaboration with suppliers to engage and being able to do this work. And sometimes they're happy to do it, sometimes they're not. It usually depends on how much you're going to buy afterwards. Characteristics of technology and design. So clearly you get this smart device, this component. You might have C, usually C. You might be all assembler, you might have FPGA. How do you manage that depending on what you get from what's inside? The other thing I think is really important in this discussion is the fact that the formal specification sometimes is performed after development. So these are COTS components, and they weren't developed formally, and now you're going to do some form of verification. So the quality of the specification really varies. Sometimes they're not very good. Sometimes they're good, but they're not formal. So you need to do them afterwards. And how do we manage that? And what's the value that this adds? And that's linked with the documentation shortcomings and the lack of specification. So these are some of the challenges of actually applying this in this scenario. My second example is about PLC-based systems. So I don't know how much you know about PLCs. I've just put a picture here from the Teleform Access software architecture, which is the main platform in APR. So I think it's not very different from most computers. It really has a platform, a hardware, you've got system software, and then you write an application software, which usually is different language you use to program that, quite often functional block diagrams or statements. So one of the things we've been looking at is using model checking to prove the application code for these systems. So I think you all know what model checking is. So I'm not going really to go through this. But these things, I think these things that model checking should really be useful for this type of systems. I think one is sort of pretty basic. So if you program them using function block diagrams, which are very close to state machines, which for me just sort of calls up model checking. Why don't you just transform this into a model and then prove the properties? So having said that, there's not a lot of applications of model checking at large on these industrial systems. There's some examples of CERN. So CERN have been pushing that and using PLCs for some of their applications. But I think we did some work a while ago on Harmonics, which is a European project, again on using model checking. But it was a research project, and it looked at had an example, and it found it. But I think the most exciting thing is really the work that has been done in Finland. So in Finland, they've been using model checking for a few years now on proving the application for the runs on the PLCs for the most critical systems. And there's model checking with SAT solvers. And they found errors that they hadn't been found using the sort of normal verification activity, which is very heavily based on testing. And I think it's really considered now normal in Finland to use model checking on this for the protection systems. And it's quite interesting, the type of things they found are the ones that are typically things that don't happen very often. And I think spurious actuation is really interesting. So spurious actuation is when the protection system, so the protection system shuts down the plant when things go wrong. So it's your last defense. And if you shut it down, and you didn't need to shut it down, there's safety implications. So you don't want to do it. And that's what we call the spurious actuation. And that's very difficult to test. And so some of the examples of things I've found, model checking was where the logic was wrong because spurious actuations. The other thing that is interesting, and we found that in one of the examples we worked before, is timing issues. Because testing, well, you test within a certain time frame that it might not be exactly the same time things are going to happen in the plan. And because model checking looks at all the scenarios, you can actually find issues with timing that are very difficult to find in testing. So this table is actually from someone in Finland who's been working on this, and it's really becoming, people really starting seeing the value of model checking. So what we're doing at the moment is sort of on a mission of trying to get the UK nuclear industry to consider model checking for this type of verification. And working with people in Finland that have been doing that for a long time, known for a long time, trying to explain to the UK industry what this brings and what's the value. And so we need to build some successful examples. So there's some of the discussions earlier on how do we persuade people there's the value. I think there's the examples in Finland, which is great, but now we need to bring it here and have some case studies where people start acknowledging this is really useful. So there are some challenges which I think is important to bring here today, which is a lot of the industrial systems, you're not influencing the design and development from the beginning. So having formal specifications and large is great when you're starting a day one and you write a formal specification. But a lot of the systems, they exist already, or they're based on codes that exist, or the responsibility for the safety assurance is separate from the developer. So if I'm a nuclear licensee and I want to prove that my application is right, I'll need to get the supplier to engage with me and be able to support that. So there's this boring non-technical challenges that I think are really important if you want to see this deploy at large. How do you bring this boundary, break these boundaries? How do you bring different stakeholders together to get this to work? So, summary. Lots of time for questions, excellent. So, in general, the regulations say, yes, you should do some sort of formal stuff. It doesn't really tell you what it is, how much you do it. So there's a level of flexibility there, and you need to explain why you're doing. So the goals are, they're there, but they're quite flexible. I think some of the things I was trying to bring in today is you need to bring in issues with IP, with getting suppliers to engage, getting suppliers to share IP, where are things developed. So I think that's really important, but also the importance of the technologies and what languages, what architectures, how things are implemented and what's feasible within those parameters. I think digital systems are really increasing in nuclear. I think you've probably all seen, I think there's on the slide earlier, nuclear seems to be on the main line at the moment. It's going to solve all the climate change problems, or some people claim to. So there's a lot of interest in building plants cheaply. They need to be cheap and quick, otherwise people are going to give up. And part of the strategy is to have more digital systems. So we need a way of justifying digital systems effectively and efficiently. And I believe formal methods can be a way of doing that. So how do we push that into mainstream or state of the art? So I think that was my presentation. Thank you.